Alright, this is the final part for the linear algebra part of engineering math. We're going to be talking about two things. Multiplicity of 2, so find the eigenvectors of a matrix that has a repeated eigenvalue. And there's two cases, and we're going to cover them in this video. Alright, so if you read the question, it actually gives us our eigenvalues. And when it says multiplicity of 2, that means that this one, there's two of them. So I'm going to say lambda 1 is -4, lambda 2 equals 2, and lambda 3 equals 2. Now it has it as lambda 2, just lambda 2, and there's two of them, but I like to call it lambda 3 just to differentiate. So A is asking what's the characteristic polynomial. It's really not difficult. You just put it back into its forms. So it's going to be like this, and that's it. That's all you have to do for part A. Is characteristic polynomial. You set equal to 0 if you want. It's perfect. You don't have to distribute, which makes life very nice, very easy. Now, as we always do to find the eigenvector, we just plug in the minus lambda across the diagonal. So it says corresponding eigenvectors, this S is there because there's two lambda 2's technically. So we're going to do -4 minus, and lambda 2 is 2, so -2, 6, -6, we set it equal to 0, 0, 0, and now we're at -6, 8 minus 2, -6, -6, 6, and -4 minus 2. Alright, so that'll simplify to give us -6, 6, -6, 0, -6, 6, -6, 0, -6, 6, -6, 0. Now I don't know if you can tell, but they're all exactly the same. So then we can just say row 1 minus row 2 equals row 2, and row 1 minus row 3 equals row 3, and then we're left with -6, 6, -6, zeros everywhere else. Alright, and just for simplicity, I'm going to divide by -6, 1, -1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Alright. Cool. Alright. So, case 1, like I said, when you're on multiplicity of 2, two things can happen. You can end up with one row of zeros when you reduce, or two rows of zeros. And this is the case where you get two rows of zeros. So we have two rows of zeros, so now we know x minus y plus z equals 0 from that first line, or x equals y minus z. Now we only have one equation, three unknowns, which means we can now have two arbitrary values. So y equals arbitrary, z equals arbitrary. Now my suggestion is to set one of them equal to 1 and the other one equal to 0. So when you do that, now you're left with x equals 1 minus 0, which equals 1. So that eigenvector 2 is going to be 1, 1, 0. Now, since you have two arbitraries, to get the eigenvector 3, since you plug in all the same stuff, you'd end up with the same answer, but you need it to be completely different. So for lambda 3, we're going to set y is an arbitrary, and we'll set it equal to 0. So we just flip-flop the y and the z. We'll set it equal to 1. And this makes x would then equal 0 minus 1, which is -1. And eigenvector 3 would be -1, 0, 1. And now none of these, no one can say that you can make eigenvector 2 equal to eigenvector 3. And then the solution just requires you to get the eigenvector 1. So if we go here instead for lambda 1, we get negative 4 plus 4, 6, negative 6, 0, negative 6, 8 plus 4, negative 6, negative 6, 6, negative 4 plus 4, 0, 0, and 0, 6, negative 6, 0, negative 6, 12, negative 6, 0, negative 6, 6, 0. Now, I don't know if you can see, but row 2 is row 1 plus row 3. So you just see that will go to 0, but the easiest way to do these is to try and get it to row epsilon form. So I'm going to flip these guys. Yeah, why not? I'm left with negative 6, 6, 0, 0, 0, 0, negative 6, 12, negative 6, 0, 6, negative 6. So now row 1 minus row 2 equals row 2, negative 6, 6, 0, and negative 6 minus a negative 6 is going to be 0, 6 minus 12 is negative 6, 0 minus a negative 6 is going to be 6, and then 0, 6, negative 6. So as you can see, row 2 and row 3 are multiples of each other, so row 2 plus row 3 equals row 3. We're left with, come on, we're left with negative 6, 6, 0, 0, negative 6, 6, 0, 0, 0. Divide everything out, we're left with 1, negative 1, 0, 0, 1, negative 1, 0, 0, 0. Alright, so now that means that y minus z equals 0, or y equals z, and x equals y. So z is arbitrary. We'll set it equal to 1, which makes y equal to 1, which makes x equal to 1. So eigenvector 1 is 1, 1, 1. Now, the solution, I'm just going to do this one time, or is like we did in the other time. It's going to be y equals, or I guess in this term, it's x equals. So it's x equals c1 e to the lambda 1 eigenvector 1 plus c2 e to the lambda 2, lambda 2 t, I believe, yeah, t eigenvector 2 plus c3 e to the lambda 3 t eigenvector 3. So in this case, x would equal c1 e to the negative 4t 1, 1, 1 plus c2 e to the 2t, and then eigenvector 2 is 1, 1, 0, and plus c3 e to the 2t negative 1, 0, 1. Let's do the second case. So it tells you again the eigenvalues. So then the corresponding polynomial is going to be lambda minus 1 lambda plus 3 squared. Because again, multiplicity of 2 means that the second one that was said, there's 2 of them, so we can just square it. And then just you can have it set equals 0. And now the eigenvectors corresponding to lambda 2, we just plug it in across the diagonal like we've always done. It's going to be 2 plus 3, negative 5, 4, 0, 5, negative 8 plus 3, 4, 0, 4, negative 4, 1 plus 3 here. Alright, well from here we end up getting 5, negative 5, 4, 0, 5, negative 5, 4, 0. So those rows are the same. Now we get 4, negative 4, 4, 0. So from here we do row 1 minus row 2 equals row 2. we're left with 5, negative 5, 4, 0, 0, 0, 0, 0, 4, negative 4, 4, 0. So now we want to do row epsilon, so we want to make this guy 0. So the next thing we're going to do is we're going to do multiply this row by, I'll multiply this one by 4 and this one by 5, just so I don't have fractions. It makes my life easier. So then that'll give us 20, negative 20, 16, and 0, 0, 0, 0, 0, and then 20, negative 20, and 20. So now we can do row 1 minus row 3 equals row 3. We're left with 20, negative 20, 16, 0, 0, 0, 0, 0, 0, 0, negative 4, 0. Alright, so from here we could redivide and rearrange things to be left with 5, negative 5, 4, 0, 0, 0, 1, 0, 0, 0, 0, 0. So now we know one thing. Z must be 0. Okay. So now we know that x, 5x minus 5y plus 4z equals 0. Since this is 0, it doesn't matter. Or 5x equals 5y, or x equals y. Now, here we only got one row of zeros, where before we got 2 rows of zeros, if you notice. Over here, we got 2 rows of zeros. Now here's how we're going to do it when we have 1 row of zeros. So we're going to get our first eigenvector the same way we got the other one. So we're going to set y equals arbitrary, which equals 1, then x equals 1. So then eigenvector 2 is going to be 1, 1, 0. Now here's where it gets a little iffy. Let me move this stuff over. Shrink it. Got left behind. Oh well, whatever. Alright. So we're left with this as a lambda 2, but we can't change anything we change the arbitrary value to will change the x and it'll just be a multiple. So I have to do something different. So lambda 3 is going to look like this. Let me just explain what eigenvector 3 is going to look like. It's going to look like w plus lambda eigenvector 2 times t. Okay? So we have part of it. Now we have to find that w. Now to find that w, the only thing we do is we plug in our eigenvector 2 in right here instead of these 0, 0, 0. So let's just do eigenvector 3. I'll show you what I mean. So here we'll do lambda 3. We have 2 plus 3, negative 5, 4, 5, negative 8 plus 3, 4, 4, negative 4, 1 plus 3. Instead of having a 0, 0, 0, we're going to set it equal to 1, 1, 0. And the solution to this will give you w. So now we're left with 5, negative 5, 4, 1, 1, 5, negative 5, 4, 1, 0, 4, negative 4, 4. So as you can see, row 1 and row 2 are still multiples of each other, which makes sense because it should work. Should be able to solve this system. You're always going to get row zeros. So now we're left with, and we're just going to do 5. Man, my 5s are looking weird today. 5, negative 5, 4, 1, 4, negative 4, 4, 0, 0, 0, 0, 0. I just moved that, made that row of zeros. And then from here we can just do the same thing, multiply by 4, multiply by 5. We're left with 20, negative 20, 16, and 4. and then this will be 20, negative 20, 20, and 0, 0, 0, 0, 0. Now you'll see when we do row 1 minus row 2 equals row 2, we'll be left with 20, negative 20, 16, 4, 0, 0, negative 4, and 4, 0, 0, 0, 0. So now we're left with, if we just divide stuff out, we're left with 5, negative 5, 4, 1, 0, 0, 1, negative 1, 0, 0, 0, 0. So y, sorry, not y, z equals negative 1, 5x minus 5y plus 4z equals 1, or 5x minus 5y equals 5, or x equals 1 plus y. So now we can set y equals to arbitrary. I'm going to set it equal to 1, so then x equals 2. So w is not eigenvector 3, this is w. It's going to be 2, 1, 1, negative 1. And so that means eigenvector 3 is going to be 2, 1, negative 1. Sorry. 2, 1, negative 1. Plus your eigenvector 2, which was 1, 1, 0 times 2. And that's the only difference between multiplicity of 1 and the two different cases of multiplicity of 2. If you get 2 rows of zeros, you just change the 2 arbitraries, flip them. If there's 1 row, you get a little more work and solve for w. And the rest of the problem is the same as the problem before. Let's do complex eigenvalues. So this is going to usually be a 2 by 2. And so let's say, okay, if it tells you lambda 1 is 3 plus 2i, what would lambda 2 be? And if you remember from all our past stuff, there's always, when there's a complex, there's always a plus and a minus. So that means that lambda 2 is going to be 3 minus 2i. Right there, you already answered A. Alright, so B, let's find the eigenvectors. So we'll plug in lambda 1. So here we'll have 2 minus 3 plus 2i, negative 5, 1, 4, minus 3 plus 2i, so equal to 0, 0. We're left with negative 1 minus 2i, negative 5, 0, 1, 1 minus 2i, or minus 2i, 0. And knowing that the determinant's 0 means that they're dependent, which means that they're multiples of each other. You can do the complex math with it, or you can just know that in a 2 by 2, when you plug in the lambda, there's always, you can just make one of the rows 0. Alright, so in here we know negative 1 minus 2i, x minus 5y equals 0, or x equals 5y over negative 1 minus 2i. So it would be the easiest thing to set y equal to make x a simple answer. So y is arbitrary. We'll set it equal to the denominator, this guy right here. So that'll be negative 1 minus 2i to make x equal to 5. So we write our eigenvector 1 is going to be x, so 5 over y, which is negative 1 minus 2i. But we want to write it like we always write complex things. So we're going to have lambda 1, eigenvector 1 is going to be the real vector, so 5, negative 1, all the real values, plus all our imaginary. So here we have 0i, here we have negative 2, and that'll be I. Alright, so what do we know about complex stuff. It's always plus or minus. So eigenvector 2 is just going to be 5, negative 1, minus 0, negative 2, I. Real simple, not hard. And last but not least, you just have to memorize this really long, obnoxious equation. So in this case, I think it's, let's just say y equals c1 e to the a t cosine bt alpha minus sine bt beta plus c2 e to the at cosine bt beta plus sine bt alpha. Alright, so you may be wondering what this alpha and beta is. So lambda equals, or eigenvalues equals a plus or minus bi, kind of like the roots, complex roots before. Now eigenvectors equal alpha minus plus or minus beta I. So those are the things. So alpha and beta are vectors, a and b are just constants, and it's just plug and chug from there. We have our alpha, we have our beta, we have our a, and we have our b, and it's pretty straightforward. So now we'll have y equals c1 e, and then I believe it was, so a is going to be 2, b is going to be, a is going to be 3, b is going to be 2, so 3t cosine 2t alpha, and alpha is going to be 5, negative 1 in this case, because it's the real portion of the vector, minus sine 2t beta, which is 0, negative 2, plus c2 e to the 3t cosine 2t times beta, which is 0, negative 2, plus alpha, plus this time sine 2t 5, negative 1. And as long as you memorize that, it's pretty set. It's not too bad. I got everything. So there, we're left with our answer there. And that is how you do complex roots.